My name's Jacob Groundwater. I work here at New Relic. I used to work on the Node agent, so I used to work on benchmarking and performance tracing and profiling Node.JS. I did that. It was great. I got the opportunity to move to our product research team, which looks at new initiatives on things and just kind of experiments, does crazy stuff. So I've been doing that for about 5 or 6 months now. It's been a lot of fun. And I got that role because I kind of just am a crazy experimenter on my own. And I guess they like that, so they wanted me to do it at work as well. So one of the crazy experiments is what I'd like to share with you today. So who's heard of RuntimeJS? Anyone? Hands up. So a few people, and don't worry if you haven't, I'm going to explain it. Anyone heard of Node.js? About the same. Okay, cool. So Node.js was something I worked on a while ago where I just said, hey, I wonder if I could replace the whole Linux userland with Node and modules from NPM. And I hacked on that for a while. It was pretty fun. You can check it out. There's another guy who's picked that up, and he's kind of doing more work on it. But then I got interested in this other project called RuntimeJS. And RuntimeJS is it's actually replacing the kernel part. So it's running JavaScript in your kernel. And we'll go through that a little bit if you don't know what that means. So I've tried to do this talk before, and it doesn't work if I do it like a textbook where I go introduction to kernel programming, stuff like it's super boring, and some people there's a spectrum of, oh yeah, I already know this, to I have no idea what any of the words on the screen mean. So what I've decided to do is assemble the questions that I usually hear, and I'm going to answer them. Now, at any point, people can maybe ask a question, and then once we all kind of get the feel for the context around this project, we can jump into a demo. So I'd like to give you enough context so that when I print something to the screen, you see all the pieces and the gears clicking behind the scenes. But if we do that right away, it doesn't look as impressive. We got to go through a little bit of setup, and then we'll get there. So I should credit Serge. He was the original creator of Runtime. Really brilliant guy. Too brilliant for me, so I actually had to scale back a little bit so that it was more accessible for me. So what you're going to see is kind of the scaled back version of it. So he's working on, I think he's doing it part-time right now, but he's probably way ahead of where I am right now. So what is runtime? So the simplest way to explain it would just be, if we have our metal layer, which is the hardware, instead of Linux, we're going to run runtime. Runtime is talking directly to the hardware, and what that means is it's talking directly to x86. So that's its interface. And then on top of that, we have JavaScript. So some things you might notice in here are there's no file system, there's no networking layer, there's no anything you're normally used to when you're dealing with the when you're dealing with a computer system. It's all gone. So another question I've heard is this like Docker? No and yes. I mean, no, Docker, the way Docker works is you're running an app on this kind of Docker layer, and that sits on top of Linux. Runtime, again, is no Linux. It's touching the metal. It's calling the x86 code. It's telling the hard drive what bit to write to what sector. So how is this different from Linux? So when you run a typical Node app, your app will talk to the distro and libc. And through there, it might say, I want to write this amount of bits to this file. And this file might have a particular name. So that'll go through the various layers. And the Linux layer will interpret OK, you said you wanted to write to home user Bob. I got to figure out where those bytes go on the disk. That's the kernel's job. So in runtime, you would actually have to write that yourself. If you're hacking this, you write that bit, and you would write it in JavaScript. So one of the demos I'm going to give is uses QEMU. So this stands for, I think it's quick emulation. You can install it on your laptops with Homebrew if you have a Mac. And it's going to provide a virtual hardware. So you can run all this runtime stuff on top of QEMU. And it's kind of providing the same as if you had just the raw hardware there yourself. The reason it's handy is you can edit something in your editor, hit save, reboot it in QEMU, and you'll see the change. You don't have to copy it to an SD card, move over here, click it in, boot it, oh, error, and then keep going like this. So it's a real time saver. It gets things moving quickly. So how does Linux boot? This is not accurate if you actually know how Linux boots, but it's good enough for the point that I'm trying to get across here, which is if I want to get to kind of the boot screen here, I get my Linux distro, and my kernel is going to be loaded onto the system, and it's basically code that's put into memory, and the system will say, OK, kernel, start executing, and then it gets to decide what to do. And usually what it does is there's this initrd file, which is like, imagine if I took like a tarball and shoved it in memory and said, kernel, here's your in-memory file system. From there, what it does is it's going to like check out what hardware you have, decide what maybe drivers it needs to load, does all sorts of really good stuff at that point. And then you eventually get your system. So the reason I drew this diagram this way, which is horribly inaccurate, is because I wanted it to line up with this one, which is the runtime JavaScript version. So what we're going to do here is, so there's the runtime code, and you can compile that to a binary. That's your kernel. That's your little tiny kernel. But this kernel does barely anything. It doesn't provide a file system. It doesn't provide all sorts of other stuff. What it does is it enables you to write those in JavaScript. So what we're going to do is, if you've ever used, well, remember, we have no file system, so I can't use like require from Node. But what I can do is use this project, Browserify. Browserify will take like all of your files that are laid out, and it'll bundle them all together, kind of like a tarball. So each file can reference and find each other. So it's kind of like a tarball, and then that becomes the new initrd. So it's going to shove that into memory. It's going to run the binary, and then this is just basically going to eval that big file, and then you're off to the races. So I hope there's another slide that explains, maybe not. If you're running in JavaScript, you're in like a sandbox. You can't actually think about your web browser. Your web browser can't write to your home directory. It can't send bits out of the network card. V8, which is the engine which runs JavaScript for the engine we're using, V8 can pass in special functions to JavaScript, and that's how you access the outside world. So it could pass in the Ajax function, and that function is now special. It can access the outside world. So we're going to do a similar thing. We're going to pass in a few special functions that access the hardware, and then JavaScript is going to go and do whatever it wants with those. So why? Great question, right? I get asked this all the time. I just thought it would be cool to npm install the TCP stack on your kernel. Because maybe in one environment you go, yeah, TCP is great. And maybe you're in another situation where you just want to experiment. NPM is great. You can kind of pull pieces out and together. And I would love to get to the point where we just started building kernels kind of like we build web browsers now, web servers now. Because if you remember, I don't know, maybe 5 to 10 years ago, everyone just used Apache. It's like, I want to write a web server. No. You use Apache. Apache will call you, and you write all these complicated rules to tell it when to call you. But we've changed. We got better tools. We got more powerful primitives to work with. And now we just write the web servers ourselves. I'm just going to throw this HTTP parsing lib on top of this socket, and we're just doing it now. So maybe someone much more brilliant than me can kind of finish this and go, oh yeah, well, I'm just going to figure out how to make this truly modular kernel where you're just programming the kernel as you need it. So yeah, what are you trying to accomplish? That kind of was what I was answering before. I just want to make a kernel by installing user modules. So you wrote this well-isolated module that handles some networking algorithm or it could be meshnet stuff. If you really want to go crazy, it could be a kernel that mines bitcoins or something. I don't know. So how can you use this? So what I did was compiling the source is really difficult, and you have to learn cross compilers and things that you probably don't want to spend your Saturday evening doing. So I pre-compiled my snapshot of it, and I wrote this little Node tool called Runtime Playground. You can install it, and it's just going to check if you have QEMU installed. But Runtime Playground comes with everything else. So it has the binary, the kernel binary that you need, and it also has a little demo set of JavaScript files that it'll run Browserify on and bundle and execute. So you can literally, in the time I'm talking, if you had your laptop and QEMU doesn't take more than a few minutes to install, you could just start hacking on a kernel yourself. In fact, we're going to do this. Another one that I get asked is, will this run Node? So the answer is both yes and no. Yes in that it could run Node, but no in that it doesn't right now. And the reason why it doesn't is if you look at the Linux side of this, all of this file system, process.fork, networking libraries, all of libc, DNS, like that doesn't exist yet. Like someone had to code all of that and put it in the kernel or in a driver. None of that exists on this side yet. So you need this node polyfill. So another question that I get is, can I write a web server in it? So you would need kind of a net polyfill. You would need to implement TCP/IP. Sounds horrible, right? But that's the point of this whole project, is to go in and get your hands dirty, but do it in like a language that you never maybe thought you could do it in. So the guy I showed at the beginning, Serge, he was actually working on this a little bit. And he probably got way further than I would ever get. But I'm going to check it out, see what he's done. I'll probably attempt this at one point and, crash and burn. But it's all about the fun. Can I use a file system? Same thing. You have to implement it. This would be a lot easier. If you think about it, what you need to provide is the Node FS API, which isn't that large. You could even just provide some of it. And then you could just store the file system in memory. Like, you just make it up. Or you could, maybe if you got good at interfacing with bits of the hardware, you could then start writing it to disk or something like that. But this part's a little more manageable. Like, the networking layer is the beast, I think. So will this run on a Raspberry Pi? I get asked that. People think, they see JavaScript, Internet of Things, and they see it like the Tesla, it's running Java. Could I run that on the Raspberry Pi? So again, the answer is yes and no. No in that it doesn't currently run, but yes, it could. And the reason why is that runtime is actually, the JavaScript layer is the bit we're going to hack on tonight. Runtime is the precompiled bit or the source. You can find it online. And it's got C++ and like assembly code in it. Now that assembly code is like fixed to the x86 architecture right now. You'd have to essentially take those bits and write the ARM version of those, and that would be what the Raspberry Pi has. So totally possible. I don't think I would know how to do it, but I'm sure someone would. But yeah, so this could run if you just replace that one bit. As far as I know, V8 will run on a Raspberry Pi. Yeah, it runs Linux, so of course it will. Okay, so this part is actually probably better left for, that's kind of your question there, but I'm going to leave it because I think I'd like to do a demo right now. So do I have my Alt tab? So I think when we're talking about old school hacking, we need an old school hacking terminal. So I have this Runtime Playground executable, and if I hit enter, it kind of gives you some info. And I can say Runtime Playground in demo. And what this is going to do is it's just going to call QEMU with all the right arguments. This is the QEMU window. So this is like the console for your old school window. And you can see, welcome to runtime. Oh, that looks great. Hey, it even lets me type. That's a little further ahead. I actually wanted to build that up. So let me cancel this. And don't ask why mate doesn't go to TextMate, but goes to Atom. So this is a JavaScript file. This is going to be like our init.rd, and we're going to hack on it right now. So this is the demo file that you'll get if you go like Runtime Playground init, and it'll write it for you, and then you could just start hacking. And it's going to give you a little bit, and then you got to kind of do the rest. So just as a quick example, what I wanted to show you here is I commented out a bunch of stuff. I'm sorry, this is going to be not a super like a Substack level live coding where it all flows from memory. I have a lot of stuff commented because I forget these bits. So we're going to kind of fill it in as we go. But what I'm going to quickly do, and we should be able to do this in not too long, is build a little REPL. So right now, one thing I want to emphasize is that there's actually nothing that knows how to talk to the screen right now. There's like literally none of that. We have to write it. But the way QEMU works, and the way this differs a little bit by system to system, but typically when the system first boots, you'll have your screen will have like a VGA buffer, which is a section of your memory in your main memory that has like a one-to-one correspondence with the pixels, or if it's in text mode, the characters at each part of your screen. And if you go into memory and you write to those sections, it's actually going to update on the screen. So these bits here are kind of like the calculation for where that is in main memory. So at this memory address is where our VGA buffer starts. Each cell, like each character, is going to be 2 bytes wide. One of the bytes is the letter, the ASCII letter. The other one is the color. And then it's got 80 columns, 25 rows. So this will tell you how big of a section of memory that VGA buffer is going to occupy. And if we write to it, we can do it. Now you may be asking, this is JavaScript. I don't have raw memory access. How can I write to that section of memory? So V8 has, essentially what I'm going to do is that's one of the functions I'm going to pass in. So what I'm going to do is I wrote a function called buff for buff, and like let's call this VGA is equal to buff, and it's going to be start size. And buff is just a global here. It's one of the functions I passed in, and it's going to take the 2 numbers I gave it, allocate an array in JavaScript that starts here and ends here. So now when I write to that array in JavaScript, I'm actually writing to that section of memory. So I'll give you a quick demo. If I just run this run init.js, if I just run this right now, there's actually no code, and it's just going to be like nothing. Nothing happens. It's a blank screen. So let me go back. And what I'm going to do here is I'm going to say for var I equals 0, I less than VGA.length. Actually, wait, I also have to do this. If you know about typed arrays, then that will mean something. Otherwise, don't worry about it. And I'll say VGA I is equal to, so here I'm going to put a hex code. It's got to be 2 bytes. So let's say blue, and I'll put the character, I think that's a capital A. And if all goes well, we should see capital A's. Oh, wait, I wrote the foreground and background the same color. So this wrote to the screen, made it all blue. Let's make the background a different color and run it again. Yeah, so we just wrote like kernel hacking 101. So let's go back to here, and what I'm going to do is I'm just going to do some live hacking, and feel free to ask questions along the way. So rather than, this is where I'm going to cheat a little bit. I'm going to like cooking show, pull the finished turkey out of the oven. What I'm going to do is comment this out, and I wrote a little screen driver, and it's in this screen.js. It's nothing special, but it's just something that I pre-did all the array calculations for us. So it's going to handle like wrapping, new line, but all it is just some math that puts it in a different spot of memory. Okay, that's the important part here. So screen, I wrote a few things like screen.write, and that's going to iterate over each character and move forward 1 every time and calculate what number to do. But let's try this. Let's just run that. Welcome to runtime. So there you go. The screen driver is working. Let's do a little more. Okay, so let's write a function prompt and screen.newLine, and then screen, and that's just, again, it's just a calculation to move where the cursor would be, right? And I don't know, what's a cool prompt? You know, this, yeah. Let's run it again. Oh, I didn't call prompt. There we go. There we go. So, but the thing is, like, I'm typing, nothing's showing up, right? So next question, how the heck do we read the keyboard? So the way CPUs work, and we have to learn this a little bit, is that when you hit a key, something called an interrupt gets sent to your CPU. And the interrupt basically, no matter whatever the CPU is in the middle of doing, the interrupt will say, no, 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 pay attention to me. And it immediately jumps to kind of a predetermined block of code. And that block of code's job is to handle the interrupt. What you generally want to do is jump to this, handle the interrupt, and then jump back. And you continue on your merry way. It's really fast. So when you press a key on the keyboard, this interrupt's going to come in. And this is remember when I had the ASM C++ bit on my diagram? This is getting handled there. And I can talk about why it has to get handled there maybe after. So what it's going to do, though, is going to go, hey, there's an interrupt. And then it's just going to put that onto like a queue. So if 10 interrupts come in, there's going to be 10 items on the queue. Then in JavaScript, what I'm going to do is pass in a function called poll. interrupt equals poll. And poll is just going to grab the last interrupt off the screen. So what I'm going to do is say if the interrupt is equal to 1, let's just screen.write a dot. So this is running in a while loop, so it keeps going on forever. And it's going to keep polling to see if there's interrupts. So now if I start typing dots, OK, now I'm typing, right, and nothing's happening. This is more like low-level stuff you have to know and love. When you get the interrupt, and I don't know the details of this, you have to acknowledge it. And it'll stop issuing them if you don't acknowledge them. So I do have code for this, and it's this in B. And that's like, basically it means like read in a byte from some hardware. And you have to specify what piece of hardware it is. And it's in B 0x60 refers to the keyboard. This is just like magic, kind of magic, but it's documented. And I'm just wrapping a simple assembly function. So num here is what's happening is poll is saying, hey, there was an interrupt. And then if there's an interrupt, I'm going to say in B, which means read in the key that got pressed. So that's just a number. Now, what I want to do is I want to translate that number to a character. So I wrote another module up here called map. And let me go to this up here, map. And it's just a big array of characters. And all I'm really doing is mapping from what the keyboard number would send to whatever the character would be. So it's just, again, it's just some math. So let me go down to here and say key is map the number. And then if key screen.write key. Now let's try this. Before weird stuff was happening, but let's try this. OK, I'm going to press J. Yeah, all right, J. Oh, so I pressed enter, and everything blew up. So let's go back. And if key, well, maybe I should say if key is new line character, then just do prompt. And then else if key, write the key. And then else screen. No, I'm not going to do an else here. OK. Let's run it again. So hello. Oops, I got to put my hello. And then enter. Yeah. Goodbye. Yeah. So we're just hacking on some Node modules, but we're like writing the core bits of like how you would, initially build these systems from the kernel level. And this is the part that I think is really cool. I guess so. I'm happy to talk about this a little more at the end. Anyone can come over, and if you have your laptop, we could literally get you started hacking tonight. If I had a goal, it would be to get you started hacking tonight. So I will. How am I doing on time, by the way? Because I actually have no idea. OK. So if you want to find out what a syscall is and how it's different in runtime, you will come see me. Thank you, everyone.